Namaskar and a very good afternoon to all of you. On behalf of PRL, I, D. Palam Raju, welcome all of you who are here assembled in the K.R. Ramanathan Auditorium and those who are joining this telecast through WebEx and the YouTube platforms. I welcome all of you to this, the 113th PRL ka Amrut Vyakhyaan. In 1947, PRL was formed, and after starting off with the 75 years of its foundation, we started a new feature called PRL Amrut Vyakhyaan, wherein we had had a series of lectures in our 75th year. That is in August 4th, 2021, and it went on uninterrupted 75 weeks and culminated in the 75th Vyakhyaan in 23 January 5. And afterwards, we took another kind of sankalp or decision that that was a grand success. I think it had its own records of uninterrupted 75 lectures. So from the second version, from PRL Amrut Vyakhyaan 2.0, we started every month. So this is 113 in that sequence, and wherein we invite people of eminence in the fields of science, engineering, technology, arts, literature, business, and law to share their excitements in their own fields, so that we can also enhance our knowledge, listening to these experts of this varied background. And in that series today, 113th one, it will be delivered by yet another eminent scientist, Professor Pratim Biswas, who is the Dean, Engineering University of Miami, Florida in the USA. He's an expert in instrumentation and aerosol measurement techniques. And today he'll be talking to us on an exciting and highly interdisciplinary topic, lunar dust, its importance, and PM sensors for its measurement. On behalf of PRL, I thank Professor Biswas for kindly accepting our invitation and agreeing to coming here and agreeing to deliver this Amrut Vyakhyaan. To formally introduce Professor Biswas to the audience, I will invite my colleague, Professor Neeraj Rastogi. Thank you.
So, good afternoon, everyone. It is indeed my great pleasure to introduce today's speaker, Professor Pratim Biswas. I know Professor Biswas since very long time when I started my PhD. I know because he is very well-known person in the field of aerosol. I got the chance to interact with him in recent years, and I requested him to visit PRL whenever you are visiting this side of the country. And he kindly accepted my request. So big thank to you, Professor Biswas. Now to formally introduce. Professor Biswas is a professor in the Department of Chemical, Environmental and Material Engineering with a joint appointment in Atmospheric Sciences at Rosenthal School of Marine Atmospheric and Earth Science, University of Miami, Florida, USA. Prior to joining the University of Miami, he was the Lucy and Stanley Lopata Professor and Chair of the Department of Energy, Environmental and Chemical Engineering at Washington University in St. Louis, USA. He also served as the Assistant Vice Chancellor for International Program and the Director of the McDonald Academy Global Energy and Environmental Partnership, which is briefly in abbreviation is called MAGIP. Professor Biswas received PhD from California Institute of Technology, MS from University of California, Los Angeles, and BTech from IIT Bombay. He is a pioneer in the application of aerosol science and engineering to multiple areas such as air quality, energy and environmental nanotechnology, solar energy conservation, air pollution control, and medicine. He has about 500 peer-reviewed publications with H index of 105 and total citation of about 43,000. He has produced 65 PhDs, PhD graduates, and several of them are now active contributors in the field of aerosol science and technology. In many IITs, his students are working as professors. He is a fellow of several national and international organizations. He has been recognized by winning several awards, notable being the Fuchs Memorial Award in 2018 and being elected to the US National Academy of Engineering in 2019 for outstanding contribution in aerosol science and technology. There are many things other to say, but in constraint of time, I will now request Professor Biswas to please come and give the lecture.
Yeah, okay, good. Thank you. Thank you for those kind words. I'm honored to be here and had, of course, a short visit. I will definitely be back. It is so impressive. And I really enjoyed talking briefly to all the scientists here and learning about your fabulous work. In some sense, I'll be a little bold and talk about lunar dust, which is a very fascinating area of work, at least for me and for many of you, but I'm no expert. I'm humbled to see some excellent work going on, but I'm an aerosol scientist, so I will put that kind of a spin on this problem, and hopefully it is of interest. Firstly, I'm even more humbled, and I had prepared this slide. Very surprisingly, outside the dean's office, I think this plaque and this is present about Dr. Vikram Sarabhai. And we all, of course, owe a sense of gratitude. Next time, if I give a talk, I have now a picture taken in his office, and it is really humbling to even stand in that office, but I can very proudly use that picture that I visited his office. And you all are all familiar with what he said, so I'm not going to read this. The acknowledgements have to come right at the beginning. Many of my PhD students, I'm borrowing their work and will be presenting it. And the current students also continuing to do some of this work, and many collaborators. And I look forward to developing collaborations even with scientists here. And we have to thank our funding agencies, NSF, DOE, US EPA, NASA, NIH, and also industrial partners who support our work over all these years. So the outline, I will talk again, you all are experts, so please pardon me for my simplistic explanation as I start this. I'll talk about the moon and why lunar dust is important, and then just allude to its formation and some characteristics of lunar dust. The proposed mission to the moon, where we want to send back humans, and the exposure, right? We talk about air quality challenges we face down here on Earth, and this is a problem of much greater magnitude, but some very important scientific understanding is to be also, if I inhale some particles, what is the impact and why is it different and so forth, and the need for studies, and then end with some measurement methods, and we are developing some tools, and hopefully one day some of the students' work can actually go on a mission and help protect the human explorers. So the moon is of great interest. And of course, I grew up as a child here. I've lived now in the United States for many years, went as a young student. But I look back and I was thinking, there was a magazine called Chanda Mama. And I don't know, some of you are very young. I don't know if this is still published. I got this from the internet. And it also dates me to some degree. That we used to read this magazine. So the moon has always been fascinating. And of course, there are many tales to be told about the moon, not only here in India, but also the Chinese mission is basically named after the goddess of the moon, Chang'e, that they have. So there's a parallel. And these two countries are extremely historical. So when we look at it from a young country like the United States, it's just fascinating to note the rich history and how much it goes back in time. And then, of course, a scientific understanding of the Earth, the geologic history, not my field, but the moon is being studied to also develop an understanding. Again, remember our only home, planet Earth. Space exploration, we want to go all the way to Mars with humans. And it's, of course, exploring the frontiers. So this is always challenging. The moon would be a good first step as they take these big steps. Potential source of minerals, right? So this is a resource again, and we can maybe do a lot of different things on the moon. Then a test bed for technologies. This I find the most fascinating. In some sense, my work relates to environmental systems, to sustainability, but we can test bed these technologies quickly, let's say on the surface of the moon. I do a lot of work on nanomaterial synthesis. We can learn from that. And of course, we can apply what we know to these lunar missions, but more importantly, we can bring it back and improve our condition here. And there are many missions, you're of course very familiar, but only a few countries have successfully landed. And of course, I'm proud that India is on this list. That is where I was born. I'm also proud that I see USA on that list. But Apollo is the only mission that have landed humans, right? It's time now to take that next frontier. And there are a lot of challenges that are trying to be overcome and resend humans back to the moon. And this, I think, is a picture of the lander here. And these are the 12 people who actually landed on the moon, only 12, right? And so time to now take that next step. So I thought I would say that. Facts, again, you all are experts here. I don't need to say that. These are just some statistics. We only see one side of the moon sitting here on planet Earth. There's a rotational sink, low gravity, but there is gravity. Surface pressure, close to vacuum, right? Earth is 1 bar. This is 10 to the negative 15. So very interesting physics. Big temperature swings. I learned today that some of you all are doing fascinating work trying to map that out by the robotic missions that have landed on the moon. And of course, data speaks a lot then rather than estimating. Human visitors, 24 are the total missions, 12 actually walked on the moon, and robotic visitors have been hundreds, right? So, and that always assists in taking these next steps. So simple facts. There's a big program in the United States, Artemis. It keeps getting pushed back, and some for scientific challenges, technical challenges, but some for funding issues, change in administration, and so forth. And this is a good descriptive of that. Ultimate goal is, of course, to go to Mars. But the first stop is going to be the moon and human missions to the moon and stay there for a little extended period, but also very importantly, at least initially, bring back people alive and safely. So that's where many of the challenges will be appearing, and it's going to be a staging capability demonstration. And of course, as I mentioned, very importantly, surface exploration. Okay, so lunar dust is what I'm going to focus on. It's very interesting. The Apollo missions, by the time they were done in the early 70s, it was very clear. This is going to be one of the most, not only interesting, but most challenging thing to overcome. This is the Apollo 17 astronaut. His suit was all covered with dust, even as he came back to the module and back to Earth, right? So maybe you brush it off and say, okay, let's move on. But no, there are equipment. If I want to build a habitat, and even the exposure, like when they come back to mothership, they want to take off maybe some of their gear. And there are analogs here. We look at analogs with firefighters. These are first responders. They have similar issues. They wear protective gear. They're very safe when they're fighting the fire, but when they come out, they strip their clothes, and that's where they get exposure. And I mentioned firefighters. 70% of firefighters, at least in the United States, end up getting cancer. The general population, it's less than 30%, 25%. So these are real issues that we need to deal with, and a lot to learn. And the parallels are just amazing. So, but lunar dust is challenging. It's also abrasive, sharp-edged. It is electrostatically charged. It's not only a particle. Here I go out into the Ahmedabad atmosphere. We study air quality. Some of the particles may indeed be charged, but on the surface of the moon, very high charge, maybe the way it is lofted on and so forth. And people have projected and studied in great detail. There's been meteorite impacts which have ground this. And there's also growth processes. And I'll allude to some of this that we mainly study down here, but can then be modified to study up in outer space and other planetary bodies. Size range could be 0.01 micrometers to 1 millimeters. That's a size range, broad size range, many orders. So the physics itself changes, and we'll talk a little about it. Many experiential observations, data, and so forth, both robotically and by humans. And it is known that this dust is going to be a critical factor as we keep sending individuals up to go back, and much research is needed. That is the key statement that I want to make. It's not a simple problem. And how do you remove the dust if it deposits on the solar panels, for example, if it deposits on your suit? Do you use brushes? Remember, it's a vacuum type environment. Do you use electrostatics? So all kinds of work going on, electrodynamic dust shields and so forth. On the other hand, this dust could be a big resource. If they are in the nanometer sizes, here we spend a lot of effort synthesizing and making all kinds of nanoparticles, including all the way down to quantum dots now. And there's a big push, and that's an area of work that we are deeply engaged in. But is this a source of materials, right? And of course, can I do more up there? Can I have manufacturing site? So very fascinating, and one can study this to a great degree for a long period of time. I'll now jump to some of the characteristics of this dust, as much as I have pulled out, and some measurements that we have done ourselves. There's also simulated regolith, as it's called, or simulated lunar dust. I like to use the term lunar particles. Lunar, I can't call it an aerosol because there's no atmosphere there, but the lunar dust is the common term. So we do some measurements ourselves. So if you look, this is of course taken from another publication, it's cited below. There's a solar wind. Because of this intense radiation, primarily lack of an atmosphere, there could be melting, there could be a corona created, a plasma created at the surface. The net is you could even vaporize, right? You could vaporize some of these materials depending on what is happening. And that's why fundamental measurements are so important. And then once it is sort of vaporized, you might have a nucleation process. We study nucleation to a great degree here. It's the birth of particles, the air quality problem I talked about, and then it can recondense, settle, and so forth. The composition is listed. There are studies. It is location dependent. That adds to the complexity. I'm going to give just a simple generalized presentation here, but each of these is very important because depends now where will my system go and land? Will it be same as some other location? And all of these are extremely important, but these are small particles of silica, alumina, calcium oxide, lot of iron in certain regions, even metallic iron, and then of course titanium dioxide, chromium. Each of these metals or species could be of great interest for engineering applications, and we intentionally make that. Like any paint you see has a lot of titanium dioxide produced in millions of tons per year down here. So you can see the importance of some of these materials, of course, for maybe advanced technology applications. So fundamental understanding of what I refer to as gas phase. Again, please remember gas phase down here, but entrained phase, particle formation and growth. And of course, our knowledge down here is much more solid, and especially for us aerosol scientists. So there's a size-time relationship. You start with molecules. Whenever you go into the building block is the molecule. You don't take a large piece of rock and keep breaking it down, though on the surface of the moon, due to intense action, that's a good pathway. But ultimately, if you go into a molecular state, the individual state, that is a good building block. And that allows me to engineer systems to synthesize nanomaterials. And then you begin to cluster. That's the first step. And some of these could be multi-component. It's not a single pure component. So even trying to simulate a nucleation process still today, I think experimentally we've made advances, but theoretically it's often a black box, right? The classical theory of nucleation fails drastically, just to put it mildly. And then there is a certain time. These are the initial cluster formation. There is a characteristic time, if I just lump it in that form, sort of critical concentration by a certain nucleation rate. And I need to compare these characteristic times or the time involved. These are all kinetic processes. I could have then collisional growth of clusters. I could have molecule to cluster deposition. We call it condensation down here, resulting in the formation of particles, right, eventually. And then I have similar expressions. By understanding the physics, I derive equations and they become longer and longer, but it could be a collision method. Now, collision down here is dominated maybe by diffusional collision, which is due to molecular bombardment. The particles move around, or Brownian motion, sometimes used in layperson terms. Up there, it's going to be more maybe electrostatically driven, right? And so forth. So these coagulation characteristic times may not hold, and same way with condensation, but it's a good starting block for us to see. And by understanding that, of course, I can now deposit them and make very fancy structures. Maybe I make a microelectronic circuit. Maybe I make nanomaterials for drug delivery, all kinds of things that we do. But these fundamental steps are important. I can put it in another way. There is dynamic processes of sintering, crystallization. Each has different scales. Putting all of this together, it becomes rather complex. So now if I look at all the data coming from these different missions, you can see that 95% of the dust is smaller than 2.5 micrometers, right? We talk about PM 2.5 here. Now, sometimes these are debated. Maybe these are the exciting fractions. Of course, there are big rocks available, and the initial Apollo missions were only told, bring back rocks. And I remember growing up as a child, I was in school, a rock came by my school, and I was so thrilled to touch a lunar rock. But it comes back in a circle now. You're studying the fine dust particles. So more or less understood that these are fine particles, and some of them go into the nanometer size ranges, but they are very irregular. They are complex because of all those different formation mechanisms. And certain compositions or certain, like silica, might be concentrated in a certain size fraction, and that gives us some knowledge of how these were formed and things like that also, right? So, but again, this is a characteristic. There is some knowledge. In fact, people report size distributions or cumulative distributions, as I've shown here, and one will then use that. So let me start now applying some of this knowledge and taking the next step. So let's say exposure. Inhalation exposure of dust is extremely important, whether it is while you're walking around. Of course, you're suited and booted. It's a vacuum, you need the oxygen. But when you come back into your enclosure, you might want to take it out because it's pressurized and so forth. It's well known on Earth that mineral dusts are very problematic and cause all kinds of diseases. And we don't want people to be picking these up or having issues when you're exposed to it. So the lunar dust is very concerning. The exposure, of course, astronauts already face this, even during their short missions. And they have pointed this out. So we need to really have a detailed understanding of this, especially under low gravity, charged particles and low pressure. So if I look at ourselves, all of you, by the way, are inhaling particles, even in this room, per centimeter cube, you at least have thousands of particles. Just imagine breathing at 5 liters per minute. I get more excited when I talk about this. So maybe I'm breathing at 7, 10 liters a minute. This is all going in. You might be inhaling more than 10 million particles just listening to me. Of course, you're exhaling them. Some of them are staying back. It's well understood where not only the total deposition, which you see on this graph as a function of size, diameter, but also broken up by the head region, alveoli, bronchi, and so forth, right? So people use this sometimes. Maybe I want to deliver drugs, maybe through the olfactory nerves to the brain. I will deposit them in the head region. If I want to get a medication to treat a respiratory disease in the lung, I want it to go deep down into the alveoli. So you can do all of those tricks. What happens when I'm under low gravity and under charged particles, right? I have to lean on my equations, and as scientists, engineers, we love our equations. I'm not going to go into that. So we do what we call a population balance equation. It's simply a number balance expression. There are transport terms. Transport of these particles might happen due to electrical fields, due to just charge interactions. As they move, there will be collisional effects because you might have a certain concentration. So the next equation is showing that the distribution might change due to collisions. And then you take all of this into account and try to simulate if I'm around under certain conditions. Of course, it might be pressurized, but if I deal with charged particles, how will these equations change? And not much has been done, right, of this. So needs to be done to have a detailed understanding and even design the protective gear appropriately. So respiratory deposition, I'll just pick on charged particle transport. And you see those equations that I showed you start becoming longer and longer. I won't explain every term, but I need to know the ion concentration. I need to know the ion particle interaction, and then the charged particle particle interactions and so forth, and ultimately predict a deposition rate, right? The work function, which will impact how much charge is picked up. Now, some of this, we are lucky we have some samples, and this I'm talking of the scientific community and certain properties. We have a good handle on these. So I can begin to throw these into an equation and begin to do some calculations and apply it so that I get the right results and some understanding. It's highly charged, but I want to now dig deeper. Charged particle collisional growth. Is that really understood? As I said, qualitatively, there are some terms, but I need to write an ion balance equation. And the ion balance, of course, you might lose ions, you might generate ions. So these are all, I'm not getting into the details of all the terms, but one has to account for that. And many of the coefficients are not really understood well, right? Here I can do quick experiments. I will also do it with lunar dust, but there are a whole bunch of these coefficients that we need to derive expressions. For example, ion-ion, the coefficient might be alpha, particle ion eta, particle beta, and so forth, right? So how do we do that? So some of this coefficients then, I need to again take a computational step forward. I want to look at simultaneous charging and collision. Maybe I make a unimodal. These are just mathematical approximations. I push and say it's a unimodal distribution. Of course, it's an approximation. And then maybe the computational challenges become a little simpler, and I can begin to do some experiments to pull out some of these coefficients. We have very good instrumentation, at least in a research lab, a differential mobility analyzer. These are real time instruments and very quantitative. I can do mass spectrometry coupled to that, and all kinds of instruments brought to bear to get a better handle. And then I can study the effect of charging on particle growth rates, because ultimately, if I'm even being exposed to that, I want to know. I can look at it in terms of a time for coagulation, normalized by a time for charging, right? So actually map that out. So the influence of particle charging on growth dynamics was very prominent, especially under ion concentrations, which are high relative to particle concentrations. So there might be conditions when this is true, and especially at the early stages of particle formation. So it then allows me to do the analysis and come up with the expressions, right? I want to dive deeper in, like now I'm studying particle-particle interactions. I'll collaborate with folks who are good at molecular dynamic simulations, because we really need a detailed understanding of some of this. So the collisional rate or this beta factor, it doesn't come straight from the kinetic theory. In fact, there's no atmosphere out there. So with charged particle, I can get expressions of the particle velocity, but then I can do some detailed MD simulations. There are many different assumptions that go in, and we try to then modify some of these expressions. The previous MD said the dipole moments would keep going up with increase in particle size, but we saw that in a size range, it remains rather flat. So of course, one has to dig into detail and then compare these. So a lot of things go into some of these calculations, right? And the last thing, this is just a cartoon. I can skip this. Time is limited. So outdoor on the lunar surface, vacuum conditions, I can begin to apply some of this even to understand the lofting or the lofting of these particles, and maybe get some idea of concentrations. Very interesting, no drag forces to deal with, no Brownian diffusion, lower gravity. So, but of course, a lot of electrostatics, that's why I dived into some more detail. Okay, I want to get into the lab, because now, as I said, I can get my hands on simulated regolith, as they call it. If you're lucky, you can get some lunar dust, but that is much limited in quantity. So I can then aerosolize this, and I can use a plasma charging system as shown in the bottom of this top graph here. And we have tools like tandem DMAs, which can map out the size dependent charge distribution. Of course, it's just a plasma, but at least gives some idea of these charging behavior that I can then compare to all those longish equations I showed you. And I can monitor the charged fraction. I can monitor the charge distribution, the size distribution. The key thing we find is the lunar regolith, the simulated regolith, picks up a lot more charge than maybe ordinary dust that we have. And that is primarily because of the composition and maybe the cleaner composites that are available in these dust particles. So I can literally now predict, and there are different types of simulants. I can use UV light, I can use soft X-rays, and I can study charging under different irradiating environments just to get a detailed understanding. So very neat experiments could be done. This is actual experimental data now, of course, in the laboratory, which gives me some more confidence that some of the models can be developed. Ultimately, I want to challenge by doing this in a vacuum system. This is where we run into some difficulties. NASA at the Glenn facility has a fabulous vacuum chamber, but now traveling has become a little difficult. But we'll, of course, go back. So we built our own chamber. And this is work which was done with the McDonnell Space Sciences Center. They have very nice facilities. I was delighted to note one of the scientists here actually worked there. And I was a faculty member when she worked there, but didn't know her. I just met her here. So always surprises and a small world. So I can use a laser-based system maybe to electrostatically charge, excite the particles, drop the dust down, and then try to collect it and measure. So, and I want to map out the charging mechanism. So there's a size effect. There are some scaling laws. And very interestingly, we compare it then to other people's studies. And obviously these differ because it depends on the system, maybe where you do these experiments, but understanding it allows us, or it's the type of the dust and so forth, which allows us to do some very neat experiments. So this is the charging, and you can see the number of electronic charges are quite high under certain conditions as the size goes up in this range, narrow range of sizes. Okay, so let's move on. Last thing I want to talk about measurement methods. We are really blessed here that we have developed some very fabulous instrumentation. Quite a few of them are also available at this facility here on different atmospheric studies. They are in some sense very precise, little bulky, based in the lab. Many are research grade, we have to admit, but it's also commonly used now. You're going to have semiconductor facilities or companies come in here, I think, in this province, in this state. You need clean rooms, you need synthesis systems. So industry also is beginning to use a lot of these instruments. They have a larger footprint and not suitable for, let's say, just sending it to the moon, even if you could take a bulky thing out there. And the moon is a very adverse environment. But just to give you a little walkthrough, there are even in the United States and even in India now, routinely, we want to collect filter samples and, of course, meet certain regulations. But then there are precise instruments like the differential mobility analyzers. And you can see the cost starts going up, the size goes up. Some of these are real time. Some have been miniaturized. In fact, they're called dust track PM samplers. And then some are humongous because I can, in addition, also get the chemical composition. I was pleased to see There's one version of this instrument in one of the labs, Dr. Rastogi's lab. So this could go up into the $1 million cost, not to mention the size, which is humongous. Can I take these and miniaturize this, right? I want to send it up to outer space, even for applications here. Can all of us be wearing one of these sensors and walking around, not to mention firefighters and so forth? So tremendous developments in, I call it optical engineering, primarily by our Japanese colleagues, now taken up by the Chinese and mass produced. For $5, I can get a very compact device which will measure a scattering signal. And NASA loves this because they'll put 100 of these, and if it gets destroyed in a mission, let it go. We just throw it off. And we are done as long as we get some useful data. But there are different forms of this, a little more expensive, packaged nicely, and commercially available. Of course, you need the electronics and so forth to be set up. So these are available, and these come primarily due to solid state lasers, photodiodes, photomultiplier tube developments, proliferation of these, including some of my own graduates who've created startup companies. They have the first wearable version. India is putting one together. Atmos, I think, is India assembled. And there are many around, okay? And that's good. People are beginning to scream, PM 2.5 is too high, it's not safe, and we got to do something about it, a different problem. So sensors, we ourselves have used it in rural India. Now I don't need to bring $1 million instrument to a village, but we've mapped out problems. We made an attempt in Delhi. We were the first to deploy 28 of these. But of course, we got to solve these problems. What do you do with the data? That's another question. And now we are really wanting to monitor lunar dust, firefighting, and other things, right? So a lot of applications of this. Very simple light scattering principles. We are all familiar with, let's say, the me theory, because it's in a certain size range, and you can get an angular distribution of the scattering intensity. I can do single particle, and these are particles in flight, okay? These are not on a surface or not collected. In flight, I can measure single particles. That's a little more precise and needs some flow systems, but I can do an ensemble measurement, and equations are well established. And the Rayleigh theory under small sizes, me theory for slightly larger, and we can use these to calibrate these. But very important factors, everyone's making this. Most of them are not so robust and worth it, though they are low cost, but they also have to be calibrated. So many of these factors have to be kept in mind as we do it. I will, of course, quickly go through these. Laboratory calibration, I can calibrate in the field or as I'm wearing it around. If somebody else has one, we can cross compare. I can go close to a stationary monitor and compare the data. So very fascinating. And the data is, of course, transmitted wirelessly, maybe to the cloud, and I can have all kinds of algorithms. These are just some calibration data. This tells you if I have sodium chloride, sucrose, ammonium nitrate, the calibration factors are all different. The refractive indices are different, but also sometimes they just saturate. So there is a certain concentration range that this might work out. So all these can be mapped out, and one needs to do that. I can cross compare the sensors. I won't dig into the detailed data set here, but you can look at it, and people are now comparing all of them and have become well aware. Can I use it up there on the surface of the moon? Because it would be fabulous. It would give me data. It might help me protect the people. So we did a whole set of tests, again in the laboratory, taking simulated lunar dust, aerosolizing it. And of course, on planet Earth, I can turn my flows on and carry this dust around into a chamber where we place some of these sensors and compare it to the very accurate differential mobility samplers. And you can see I can get reasonable calibration factors. And these are different sensors, the data for different sensors. But as long as I have a fixed slope, I'm quite happy with it, right? Because it tells me that I can use it. I can do a mass concentration calibration, a number concentration calibration, and then potentially these could be used maybe. So we do a lot of this work. And again, the calibration factors are completely different for the lunar dust. I want to do the calibration in a vacuum environment under low pressure. So we would now make our chamber, just evacuate the chamber. This makes it very challenging because how do I sample? To sample the aerosol and use a precise instrument, I need to have some kind of flow. So it's sort of a way that we have these instruments designed to operate under vacuum condition, the more complicated and precise instruments, right? And we can get the signal ratio, and then you can see the pulse height, which is basically the scattering signal, sort of match up the diameter on the right-hand side. And we also compare it at different pressures. Though this is an optical signal, you might think it shouldn't matter as long as I'm getting the particle into the viewing volume. And we actually demonstrate that over a range of pressures, this would be pretty okay. So you do tests like that. Then you want to explore new designs. I go to the optical store and now I can buy a laser which shoots out in 3 colors. And if I can do a 3 wavelength measurement, it's going to make my reading much more precise, my interpreted dust characteristic. There are these avalanche detectors, a little expensive, but they can measure multi-wavelength signals very precisely, scattered signals. And I can then use it to interpret the data. I can do a time of flight measurement, and I can use all of this to really improve the applicability of some of these sensor materials. And eventually we put together these systems. We might also want to collect the dust particles, and simple electric fields can be used to now trap these dust particles. And again, these are some calibration curves, not jumping into the details. The inversion becomes quite complicated, but it can be overcome and done quite precisely. And you can also get some information on the sort of effective refractive index of the particle, right? So with that, again, more data at different wavelengths and the convergence, you can develop machine learning algorithms to figure out the combination of the refractive index and the particle size to give you the appropriate data. And we are now developing these tools and hopefully have a good calibration. So this is now collective calibration data for the lunar dust simulant compared to smoke particles and even to dust particles. And you can see the ratio of the different wavelengths that give you parameters that can now be interpreted very nicely, and a good correlation of the actual size to the measured sizes can be pulled out. So very promising, and we have to, of course, continue the development. But I just wanted to end now saying that some of these sensors could create a social revolution. All of us could be wearing one and walking around, and the data could be sent up to a central facility. And you can have stationary monitors. We already have them. We could put it on a drone. You don't need to fly your drone. You could put it on your trucks, and you can really map out the air quality problem. And you could do the same on the moon when you have multiple individuals and habitats. You want to find regions of safe or low particle concentration or dust concentration. Physicians are beginning to use this because if I'm an asthmatic, my asthma attack is triggered by exposure to high levels of particle concentration. If my physician can see it on a dashboard and gets an alarm, can immediately tell me to either get out of that place or come and take medication instead of being rushed to an emergency center. The concept of personalized medicine. So this is really becoming very exciting, even on down here Earth applications. And we oftentimes refer, everyone can afford it. Most of us now wear watches which are measuring our blood pressure, measuring this, that, everything. You can also measure your PM exposure now as an added thing. So I just thought, though you all are all looking at outer space, or some of you are doing atmospheric science, we really need to focus here. And I, of course, work with a lot of colleagues, many excellent studies done. The source categories are known, but to really solve the problem, every time I come, the PM concentration is going up. Sensors are now beginning to track the pollutants, but beyond reporting, we really need to implement source control technology. In the United States, it took us 40 years to bring down pollutant levels to a level that it's really safe for young children and very elderly people. China took 15 years. Some of us have worked in these systems. I think India should do it in the next 5 years. And we have to accept that we face this grave challenge here. And I thought I would end with that. And all of us are scientists here. We should work together to really deploy some of these control technologies. Sensors can detect this and help us solve the problem. And it is really, I feel it's an urgent thing that needs to be done. The solution is not that complex, right? Pick combustion sources. Let's do some control. And this is not very fancy control systems. They are available, but begin to show which ones make a difference. And many wonderful studies being done, including here, right, where the categories are known. So let us hope, and then outer space studies and developments can help us down here. If I'm going to solve the problem on the moon, I better solve it back down here too. And then I'm also an academic. I'm in fact meeting in IIT Gandhinagar starting tomorrow on, we need to educate. I feel even aerosol, very few people even know this word, even in the United States. So we take a great push. I was delighted to see Dr. Rastogi have an interest. We need to bring it down to our even school level and very advanced. We just had an Asian aerosol meeting in Bombay. I was just pleased to see 400, 500 individuals, many from different parts of India now, studying these problems, aerosol science and technology problems. So can we prepare good training material, right? And this is scientific and technical training material. I often find the fundamentals are not covered in as much detail, and we should really dig in, and not only at a few of us level, maybe at a broader level, and then bring some of these applications. And that motivates. I lectured several undergraduate students. I could see initially they didn't care what is this fellow talking about, but by the end they all got excited. And that's how you have to do it, literally in small groups at a time, right? Give people a chance to come and see these fabulous facilities like at PRL. And I'm talking now of even undergraduate students maybe taking a field trip here. Of course, we have research experience programs, and I heard that you all have it here too, and so forth. And then continue research and development. Climate mitigation, I didn't even allude to it, is a big problem and related to particles and aerosols. And nanoparticle technology is another fascinating field. We get engaged in it, and you could be innovative, entrepreneurial, and India is the startup capital now, right? So let's do some in these areas. So, and then I like to dig into history. I, of course, just named some people here. I think we should always look at the history. I mean, look at this place. I started with a quote from Vikram Sarabhai. My joy knew no bounds as I got to see his office, got to see many of the plaques around. This is very important, I feel. And same way in our own fields, we should always cover it. And I always have a slide I show. And of course, being an aerosol scientist, I claim everyone is one, starting with Newton, going all the way to Stokes, going to Einstein. And these are all folks who did the initial work to come up with these expressions and so forth. And you heard about Fuchs, Russian scientist, and we need to also popularize that and make our folks aware. So thank you very much for listening. Hope it was of some interest. Tremendous activity in the US, where I come from, Blue Origin and SpaceX. Blue Origin was always focused on the moon. SpaceX wanted to go straight to Mars. They said, why do we need to go to the moon? They have changed. So now there's some commercial competition. We, of course, have our good friends in China, and they are pretty advanced. And when we are scientists, we all work together. But, you know, healthy competition is always good. And the US, they want to get there before China does in 2030. So competition is always good. And you heard about optical device innovations that has caused a revolution in sensing. And let's do more of this and work together to improve our condition here. Thank you again for listening. Thank you very much. Yeah. If there are time for questions, I'll try to answer any questions. Yeah.
Thank you very much, Professor Biswas, for a nice talk. You have elucidated that dust is not a problem on Ahmedabad or on Earth, but it's also a problem
Oh, no, it is a
on
major
the
problem.
moon.
Yes.
And then you have also emphasized that before we actually venture into mitigating the dust on the moon, we should actually try to mitigate it on Earth first.
Yes.
And then many congratulations and kudos to your work, which you have been doing on the miniaturized sensors, wearable sensors, which will definitely be a game changer, particularly in the coming future when we have a sequence of missions, including Artemis and our own Indian lunar base station. So thank you very much for this nice talk. And I'm pretty sure that there would be several questions, both offline and online. So let us first take offline questions. Professor Bhala.
Thank you. What is that Arizona test dust?
So, you know, I think we are over-organized in the United States. We try to come up with, and it's a very good thing, we try to come up with a very systematic calibration sample. So I can go outside and pick up Ahmedabad dust and do a test, nothing wrong. But when I want to cross-compare, right, maybe there are 100 labs doing checking on dust, for example. So in the US, we call it Arizona road dust.
Okay.
It's maybe originally from Arizona. It's synthetically prepared, and it's very uniform representation of dust that everybody uses for calibration. It's just a name, but the origins might have been from Arizona. There's a lot of arid land there, and you can pick up dust. Yeah.
I thought you have taken the dust from the Arizona crater.
It could be originally from now it is synthetically prepared and supplied to everyone with uniform characteristics.
Thank you.
Yeah. But I'll look up the history of Arizona, why it's called Arizona Road, but I think it's from some of the arid regions. Yeah.
Any other question? Yeah, Neeraj.
JSC1 sample was used for Mare analog. For Highland, which sample was used?
For which one?
Highland areas
Yeah.
of moon.
Okay. Yeah, there are different. We just stuck to one of them as an initial testing. Some of it also being directed by NASA because they will do a lot of cross comparing of technologies before they select. So you're talking of different regions of,
Yeah.
we didn't do that. but they are available. But this was just a directive. So I actually have data only from this particular simulant.
Okay. And in the experimental setup, what was the vacuum level achieved?
We went down quite low. I mean, not 10 to the negative 10 bar, but I would say maybe 10 to the -5, -6, -7 bar with some larger pumps in a small enclosure.
Okay.
But NASA Glenn has a fabulous facility, which ultimately we should go there because you can do a lot of things inside it, including jet plume,
Mhm.
right? I was talking, I think, previously, because that generates dust. So you could simulate that experiment.
Okay, thank you. Thank you.
Yeah, so
Yeah.
I have a question, actually two questions from from the first part of your talk. You showed about this growth rate. The collisional growth rate was slower compared to the condensational growth rate. Is there any simple understanding of this? And second, you mentioned that the conventional theory of the nucleation doesn't work very well for the lunar dust. So what are the basically missing things?
So it actually doesn't work for down here. But the first question was, why is the collision rate slower? So just a very qualitative thing. Condensation is molecule-particle interaction, correct? So molecules are, of course, a lot more, move much faster because of a lower mass. Down here, it's just the kinetic theory of gases. It's temperature driven. Up there, it is more electrostatically driven. But the net is, it's a much lower mass. So the flux to a particle, which is the condensation process, is much faster. The collision rate is particle-particle. They are a little more sluggish in their movement. So it's slightly slower. But again, one has to carefully look at it, let's say for a lunar environment. Definitely down here, that is very true, right? The condensational rates are maybe much faster. The second question was, remind me?
Regarding the conventional theory of nucleation.
Nucleation. Yeah, nucleation fails. I made that comment for down here. Like if you go to the atmosphere, we are forming a lot of new particles. Not everything is coming directly from a source. Gases react in the atmosphere and nucleate. Now, the classical nucleation theory works well for water, pure water. And water is important, the water cycle or cloud formation. But the minute I have another species, like let's say sulfuric acid, or some even maybe a particle dissolved ammonium nitrate, the nucleation rates are very difficult and don't agree with the classical theory. Now you come to metals, you come to combustion systems, it just miserably fails. So the nucleation rate is used as a black box, often empirically, or we use a chemical reaction model to get rates for nucleation, right? And on the moon, it's a lot more complex system with some of these charged species and ions. Here also, you have ion-induced nucleation, which people try to get expressions. There, it is definitely ion-induced nucleation. So classical theory will fail. Classical theory is more thermodynamically driven with a metastable state. And again, sound thermodynamics, but unfortunately for multiple species, it fails miserably. And that is well understood. People are now using molecular simulations to get better handle. So a lot of studies are going on. But the classical theory, which may be a little easy to use, but doesn't agree quite well. So you have to have a correction factor for that. Yeah. Thanks.
Yes, first of all, thank you for this wonderful talk. My question is on the detection, on the techniques point of view. See, what are the minimum number of, grains or that can be seen in your technique, and what is the maximum number? Because there are more and you have multiple wavelengths coming in, you will get a continuum, you know.
Yes, you will get interference and
Yes,
multiple
multiple
scattering
scattering, yes, yes.
and errors. So
Right.
but that we can overcome, of course, down here with fluid mechanics, right? There it's more ballistic. So there we should rely more on an ensemble measurement in that case when you have high concentrations. But these can be used for single particle scattering detection. So the innovations in optical engineering, as I call them now, are very good. The PMT systems, they're miniaturized, but they can detect. So we have number of single particle scattering instruments, and we get them single by doing again fluid mechanics kind of arrangements. And terms of on the lunar surface, they are also thinking of making a sequence of these channels, and with the hope that maybe a particle will go into each of the bins. They will be shot up ballistically, but you will get single particles. So single particle is okay.
Yes.
Provided if I'm in the elastic region, 0.3 micrometers is my limit even today, right? Because these are visible light sources. And the upper limit you overcome by just switching to ensemble. And what you're saying, the we call it coincidence error, multiple scattering is a very serious problem, and we often try to avoid by designing flow systems. But on the moon, I can't have a flow system, at least outdoors.
Right.
Yeah.
So probably I think this works best when something is coming to detector rather than this detector looking at the dust.
Yeah.
Looking down.
This is a flow through. Even
Okay.
on the moon,
Yes.
we will design it so that
Okay. It has to
catch them.
Okay.
Yeah. Go through the system.
Okay.
Yeah. We can't use pumps on the moon.
Right. No, already, already it's minus 15. So anyway, there is, you don't, so you have few numbers there.
Yes.
But so what event makes the dust to flow? Because
Yeah, so that is electrostatically. So depends. If I'm walking around, I kick it up, mechanical forces,
yes.
and with the charge playing a role. If it is a jet plume, we kick up. So there is some fluid flow there because of the exhaust of the engine, which also lofts the dust. And that is a critical period because apparently that creates, and someone was saying in a certain region that doesn't happen. Yeah, but these are all very interesting things. Yes. But down on here, when we use the sensor, that has a built-in pump.
Okay.
It has a built-in pump. So I give credit to my younger former graduates. They have used miniaturized pumps. It has everything built in that little unit.
Okay.
Yeah. So it's really fascinating.
Thank you.
And it has all the electronics to send the data. Yeah.
So, Professor Biswas, thank you very much for a nice talk. I just want to pick your brain on you as a policymaker, maybe. Because you said that you come to India twice or thrice and you may be inhaling all our PMs. So particulate matters.
Yeah.
So see, in India, anyway, as in any developing country, we have the problem like this air pollution, particulate and gases both. And you said that US took around 40 years, China just 15 years, right?
Yeah.
And you want us to do it in 5 years. So, so we'll be very happy if we can do it. But so far as aerosol science is concerned in India, I think we have probably one of the branches of sciences where maximum number of students are involved is aerosol. Yes, I think so. No, in India. And we have so many good groups as well, right? So I think science point of view, we have pretty good understanding of the sources, where it is coming from, what.
Yes.
So when you compare to US or say China, forget China because they have different form of government. When you compare to US, what do you think India can do? Science-wise, we are lacking something, or policy-wise, we are lacking, or I think is it just implementation?
Implementation. Very simple solution. And I'll be open here. This is my home too, okay?
Yes.
We want to see it clean. Fabulous scientists, no doubt. But, as a scientist, now I'll blame my scientist colleagues a little bit. I want to use the latest mass spectrometer and understand the chemistry in even more detail. Yes, I can sit and do it in the US. Here, please go after the source. Control technology is well established. You have to tune the control technology. So there's some development research work there too. And there are people doing it, but implementation is critical. I think commercial entities, industry should be a partner. Of course, ultimately comes to also policy,
Yeah.
right?
So
And-
I think in US, it was this Clean Air Act in 80s probably, which led to, I mean, a lot of
Correct.
reduction in the
right.
atmospheric
And
emission.
started 70s.
70s, yeah.
Yeah.
So, okay.
Mhm.
So basically,
But it can be solved, and 5 years is doable. The condition is quite bad.
yeah.
If you
it
go
is.
to Delhi, Bombay, you know, if you're not wearing a mask, it's very problematic. So,
Yes. Okay,
so
thank you.
Mhm.
So if there are no questions here, we'll take up YouTube question. So there are 4 questions by Anit Swami on YouTube. So maybe we'll take a couple of them. The first question is, with sensor response varying by size, composition, or it may be relative humidity and pressure, can physics-based calibration replace environment-specific tuning?
Yes, we in fact wanted, and I of course brushed through, I wanted to present so many slides. So you want to calibrate. Calibration is experimental, but the calibration ultimately comes up with an algorithm which sits on the cloud and cranks up and corrects the data. And that to some degree is physics based, right? And nowadays people, we have ourselves used machine learning techniques because you generate large data sets. So you want physics based machine learning techniques or physics-based statistical techniques for the calibration. So absolutely right. And that's where I showed one scattering equation. You can invert that, solve that, and use the me expressions to help in come up with more robust calibration factors. Yes. And same way as they were saying pressure and other parameters. Humidity is a very important parameter, and it's already shows up in the calibration equation that people are using here. Mhm.
And the next question is, what design principle should guide next generation aerosol sensors so miniaturization does not compromise physics, calibration, or mission reliability?
Yeah, so this is a question like all of you want to know what you were breathing in this room, at least you should want to know. So I might want to compromise because low cost is important. You cannot buy a scanning mobility particle sizer and take it with you everywhere. Firstly, it's bulky. Secondly, I don't think you want to spend $100,000 just for yourself, right? Your wife will want one too. Let's pick on our spouses will want one too. So miniaturizing has a role to play, even though the accuracy is not perfect, correct? But on the other hand, if I can make it as accurate as possible, that's extremely important. But we have to understand the limits. We have to understand, yeah. So the socialization of measuring PM, and you see that in India, people are now, of course, you can see it in the atmosphere, but they will say PM 2.5 was 200, do something. So these are important, but we should make it as accurate as possible. Now, some don't, which is not a good thing. You should use the best calibration procedures available and components within that low cost range and build these devices.
Thank you very much, sir. So before we move on to the next part of this event, I have a small question,
Sure.
if you permit me.
Yes.
So in one of your slides, that is continuation to what Neeraj was asking. So you have showed 2 simulants. One is JSCA
Yeah.
and another is LHS.
Yeah.
One.
Right.
I think maybe that is Lunar Highland simulant.
Yes. Yes.
But
Yeah.
in one of your slides, I could see a significant deviation between these two.
Correct.
Is it because of the physical properties or the chemical properties?
Yeah. This we are doing the measurements down here on Earth. So it's very much just the composition and the even within that, it's the refractive index. And some of them have multiple elements. These are composites, as you know. So the way the composites are, the way the simulant is prepared impacts that. Yeah. So for this difference is just due to the refractive index difference between the two samples.
So thank you very much, sir, for patiently answering all the questions. If anybody has any further question, you can please write to Professor Biswas. So now we move on to the next part of this event, where I request Professor Palam Raju, Dean PRL, to felicitate Professor Biswas as a token of appreciation from PRL.
Okay, thank you. I hope it was okay. Yeah. Thank you very much. Yeah.
Logo.
Yes, good. Very nice. Oh, thank you. Thank you so much. Yeah. Good. Thank you. Yeah. Thanks. Yeah. Take it home.
Thank you very much, sir. So now may I request Dr. Vineet to present vote of thanks. After that, I invite all of you for a cup of tea outside the auditorium.
Yeah, so thank you very much. So this brings us to the end of this wonderful session. So first, I would like to thank Professor Biswas. So it was a one big ride through the lunar regolith to the aerosols on the giant rock that we live on. Thank you very much for giving such a nice talk, and thank you very much for answering the audience's questions. Okay. So next, I would like to thank all the audiences, both on our YouTube platform as well as the audience who are present here for listening to Professor Biswas's talk. Next, I would like to thank Professor Anil Bhardwaj, Director PRL, Professor D. Palam Raju, Dean PRL, for all of their help, guidance, and in organizing this event of PRL Amrut Vyakhyaan. Next, thanks are due to the PRL Amrut Vyakhyaan committee for successfully organizing this episode. And please do visit our social media channels to know about more events coming up in PRL, especially PRL Amrut Vyakhyaan, this event. And with these words, I propose for the closure of today's episode. And thank you very much. So you are all welcome outside for a cup of tea.